Science 20s, Mr. Wiley here. In this video, I am going to teach you about a physics concept called impulse. And to talk about impulse, first thing we got to do is think back to last week, and we learned about something new called momentum. And so we just want to recall that momentum is the mass of an object multiplied by its velocity. And that's going to give us momentum. The symbol we use for momentum is that P. I described momentum as how you would feel getting hit by an object, right? You're considering how fast the object is going and also how heavy the object is. Now, we need to understand momentum to talk about impulse, because impulse is simply the change in momentum. And when we're talking about a change in momentum, the two parts of momentum are mass and velocity. So usually an object's mass is not going to be changing. It's not growing or shrinking. It's going to be changing velocity. And so really when we're talking about a change in momentum, we are talking about a change in velocity. And when we're talking about a change in velocity of an object, we're talking about acceleration. So we can actually relate impulse here to acceleration, and when we take the mass into consideration as well, we can relate it to force. And so there's another way to define impulse, and it is the product of a force applied to an object over a period of time. So this takes us back to Newton's first and second laws. Where in order to accelerate an object, we need to apply a force. And when we look down here a little bit, we see two formulas that we can use to calculate impulse. The first formula, simply you're taking the final momentum of an object and you're subtracting the initial momentum of that object, and that will give you your delta P. Now you guys notice I've added my little arrows into these formulas. That's because momentum, like force and acceleration, is a vector quantity. That means that it's going to have a direction associated with it. And usually for us, that direction is just going to be forwards or backwards. We use positive numbers for forwards, and we'll use negative for backwards. Now, another formula that we can use to find the impulse change in momentum of an object is we can take the force applied to that object and multiply it by the amount of time that force is being applied for. And those are two ways that we're going to look at this. Now, I remember way back, so this is a long time ago, I'm dating myself now, when I was in high school. I graduated in 2001, and I remember studying for my Physics 30 diploma, and I had a big light bulb moment where I suddenly realized that all of the concepts that I was learning about were all related to each other. And you could use one formula to find another formula, and you can create your own formulas as well. So, one of the cool things that I love about physics is that all the concepts that we learn about are actually all intertwined with each other. And that's what makes physics so cool. So let's look at an example here. So here I have a ball, and this ball has a mass of 1.5 kilograms, and it's moving at a velocity of 5.0 meters per second. Now, let's say I want to accelerate that ball to twice its velocity. So I want it to go 10 meters per second. There's going to be a change in momentum that occurs over this period. And the period over which this change is happening, we're going to say it's 10 seconds. So over a period of 10 seconds, I want to apply enough force to accelerate this ball from 5 meters per second to 10 meters per second. So I want to speed it up. And when I look at the momentum here, if I do my mass times my velocity, before I apply my force, this ball has a momentum of 7.5 kilogram meters per second. After I apply my force, this ball will have a momentum of 15 kilogram meters per second. Now, I can use some math to help me figure out a lot of things, but one of those would be how much force do I need to apply over those 10 seconds to accelerate this ball. So what I'm going to actually do is I'm going to try to find the force. And something really important for us to take out of this is that when we're calculating force, force is one of the ways we can define force is the rate of impulse or the rate of change in momentum. And I mean, the other way I wrote it down here is, delta P, so impulse per second or change in momentum per second. So it's basically how fast or how slow my momentum changes is going to greatly affect the amount of force. If I want my momentum to change very quickly, I'm going to have to apply a lot of force. If I want my momentum to change more slowly, I'm going to be able to apply less force. So when I do a calculation here, and all I'm going to do is I'm going to take this formula right here, this one, delta P equals F delta T. So I'm going to take this delta P equals F delta T, and I'm going to manipulate it to solve for force. So force is going to be equal to, I'm going to divide both sides by delta T. So it's going to be delta P over delta T, or the impulse over the time. I could say the change in momentum over time. So when I do that, I'm going to actually get my momentum per seconds. So what happens is I end up getting kilogram meter per second, or a kilogram meter per second squared. Now there's another way that we define this unit, and that is, kids, the Newton. So a Newton of force, 1 Newton of force is 1 kilogram meter per second of momentum per second. Okay, so let's look at another example here. So a 4 kilogram bowling ball changes velocity from 8 meters per second to 5 meters per second in 0.20 seconds after colliding with a bowling pin. So we've got a bowling ball going down the lane. It strikes a bowling pin, and then it slows down from 8 meters per second to 5 meters per second. And it makes that change over 0.2 seconds. So let's look at the momentum before. So we want to find the P initial. So that's going to be our before. That's where we get our initial from. So just like calculating any other momentum, it's mass times velocity. Okay, and I'm going to use VI here because the initial velocity is there for me. So that's going to be my 4 kilogram bowling ball. And I'm going to multiply that by my initial velocity is this 8.0 meters per second. So when I do that, I'm going to get 4 times 8. I'm going to get 32 kilogram meters per second. Okay. Now the momentum afterward is my P final. Okay, so I'm going to do my mass times my V final. So this was my V initial. This is my V final after it strikes the pin. And I'm going to take my 4.0 kilogram bowling ball, and I'm going to multiply that by my V final, which is 5.0 meters per second. And I'm going to get 4 times 5 is 20 kilogram meters per second. Now my change in momentum here, I'm going to calculate using that first formula we looked at. So my change in momentum, which is my impulse, okay, is delta P equals P final minus P initial. And so my P final is 20 kilogram meters per second. And I'm going to subtract from that 32.0 kilogram meters per second. And I think you guys can see here, I am going to get a negative number. So I have to take 20, subtract 32. So I'm going to get negative 12 kilogram meters per second. Now, that makes sense because the bowling ball lost momentum after it hit the pin. So it makes sense that we would have a negative impulse here. Now, what is the impulse or force that is required to change the momentum? So really this question, what I'm asking for here is the force required to change that momentum. So basically, what was the force applied by the bowling pin to the ball? And in order to do that, we have to look at our other formula. So that other formula looked like this: delta P equals F delta T. I now know my delta P value. I just calculated that. And I know my time. The time of impact of the bowling ball with the pin was this number up here, 0.20 seconds. So I'm going to take that formula and I have to solve for F. So I'm looking for F. My delta P was that negative 12.0 kilogram meters per second. And my delta T is the time that passed by, 0.20 seconds. So I'm going to plug those into my formula. I have to manipulate my formula here. So I'm going to have, I want to solve for F. I'm going to have F equals delta P over delta T, right? You guys see I just divided both sides of this formula by delta T, and then on this side, those cancel out. And I'm going to plug in my value. So I'm going to get negative 12.0 kilogram meters per second divided by 0.0, oh, sorry, it's not 0.02. Not redoing the video. Okay, it's 0.20 seconds. And so I'm going to take my calculator. I'm going to do negative 12 divided by 0.2. And that's going to give me negative 60. So my answer to this problem here is going to be negative 60 kilogram meter per second, or kilogram meter per second squared. And do we remember what's another way to say that unit? It is negative 60 newtons. So you might be thinking, okay, well, how can force be negative? And so all that means is that the bowling pin applied a force against the motion of the bowling ball. So there was a force of 60 newtons applied in that direction. Okay. Now, this next piece here, we're going to do a little assignment on that. So I'm going to skip over that. And I just want to mention here Newton's third law. So we talked about Newton's first law. That's the law of inertia. An object in motion wants to stay in motion. Object at rest wants to stay at rest. Newton's second law, we talked about how the force applied to an object is directly proportional to the acceleration of that object. And the third law of motion, you might have heard it in a different way before. It states that every action has an equal and opposite reaction. So the idea here is that the force of the bowling pin against the bowling ball there was also an equal and opposite force of the bowling ball against the bowling pin. So if there was a 60 Newton force going against the bowling ball also had a 60 Newton force against the bowling pin. Okay? And we'll talk a little bit more on that. So I think that's enough for you guys. Do the practice. Let me know if you have any questions. Good luck.